In this video, we're going to go over the 9.3 notes, which is the last set of notes in topic 9. And this set of notes is all about curve sketching. So essentially what we're going to see here is we're going to see sort of the culmination of everything we've been talking about over the past several sets of notes. And specifically the way that we're going to use all of this information that we've been talking about in topic 8 and topic 9, apart from like optimization, is how to use calculus to determine features of a graph of a curve, without even knowing what the actual function is that produces that curve. And we're going to talk about very briefly, just at the end, how to use calculus to sketch from scratch the graph of a curve. So here we're going to talk about what do we do if we're given our function and we want to sketch it, usually just based off of the function itself and nothing else. Okay, so like we've seen in this previous several sets of notes, we've used graphs of functions to help verify our results, like when we were looking at, for example, intervals of increase or decrease at the end of topic 8. We would pull up a graph of the function and just verify our results. Same thing with concavity, same thing with extrema. So visualization can be really nice to, of course, see how a function is behaving overall and at certain points of interest. So whenever we're talking about a function, usually in the real world, we're talking about a function that has some sort of use to us, whether it's a function that is describing the movement of a particle or the features of some sort of financial graph or something like that. We're interested in describing the features of the function because the function means something to us. And so in a lot of cases, when we're talking about understanding the pictures of functions, they're not the easiest functions to work with. So sometimes we might be dealing with functions that we can sketch by hand relatively easily, and that will allow us to see certain features of the function. But sometimes we are not able to do that very nicely or very quickly. So for example, the f of x squared, that's a pretty simple function. We could just graph a couple points on this function and give a general picture of what the function looks like. 2x plus 4, that's just a linear function. It's just going to give us a line. Even 1 over x, that's not too difficult to sketch just by plugging in a couple points into our function. But like I said, a lot of times in the real world, if you're interested in the behavior of a function, it's hard to just graph it, especially if you're just doing it by hand without a calculator or a graphing calculator. And so it's harder for us to determine certain features. So something like f of x equals x times the square root of x plus 1, for example. That's a little bit harder to graph or a little bit harder to think about what it looks like. Or something like this, f of x equals 9x over x squared plus 2. So what we're going to see in this set of notes is we're going to combine information that we've learned from previous sets of notes with this new goal of sort of using all of this stuff we've been doing in basically topic 8 and topic 9, apart from optimization, in the realm of using that information to sketch a function and determine features of a function from a sketch. Okay, so just a couple quick things before we get started. I'm actually going to scroll through the notes here really quick. A lot of this stuff at the first couple pages is stuff that talks about basically what you need in order to sketch a function from scratch. So if you're just given f of x, these are the features or the bits of information that you can get from the function to get a pretty accurate sketch of what the function looks like. So there's quite a few things that we can look at to get a good picture of a function. But for most of this set of notes, just because this is a little bit more of the focus of this set of notes, is not so much sketching curves from scratch, but rather using features, specifically first and second derivative features and related quantities, taking those features and using them to describe information about a function given a specific graph or a specific bit of information visually. So if we go over here to page 4, we're going to see a lot of these are just problems that involve looking at graphs and then figuring out statements about a function that's related to these graphs. It's only at the very end here, and we're probably not going to have time if you're in 249 in either section. We're probably not going to have the time to do this in person in class, but we do have an example here at the end where we just sort of start with some function and we sketch it all by hand. So what I'm going to do, just so that this set of notes is a little bit easier to follow, is I'm going to focus on the important stuff, which is reading pieces of graphs or graphs about a function. And then I'm going to go back through these first couple pages in a little bit more detail, and we're going to use that to sketch the function at the end. So again, just to emphasize what I'm doing here, I'm going to skip a lot of this. I'm just going to talk about some of the features here before we start looking at the examples. I'm going to jump to these examples here starting on page 4, and we're just going to go through these, and then once we hit this last example where we're actually sketching a curve from scratch, I'm going to go back to the top of the notes here where I just indicated the curve sketching section here, and we're going to go through each of these features one by one in sketching that final graph. As far as exams go, as far as assignments go, as far as any remaining lab tasks go, the thing to focus on are these examples here where we're not sketching a graph from scratch. We're using like a graph of the derivative or a graph of the second derivative to get some information about the function. So I'll emphasize that again when we get there, but I'm going to focus on the stuff that's more relevant to us as far as the pieces of this process that we need to keep in mind instead of the whole overall, here's how you sketch an entire curve from scratch. But it is useful knowing how to do that, so we will do one example of that at the end here. Okay, so let me go back up. Sorry, there's so much scrolling. Let me go back up here to page 2 and just mention a couple things before we jump to those first couple examples. So when we talk about curve sketching, what we're basically doing in this course is we're using our current knowledge of information about a function, including information we can get from calculus about a function, to get ideas about certain features of the function, which we can use to help sketch the function. So I'm going to go through this list real quick, and then I'm going to go to the examples. But essentially, there's a good amount of features we can consider to give us a good, accurate picture of how a function behaves. These first 3 things here, the domain of the function, the intercepts, and the asymptotes of the function, these are all things that we can figure out just by looking at the function itself. So just by looking at f of x and some of its features. So there is actually quite a bit of stuff we can get just from the function itself. But of course, there's a lot of other features we can get from calculus, specifically the first and second derivatives. When we talk about information from the first derivative, so the first derivative of f of x, this gives us information about where our function is increasing or decreasing, as well as the location of any extrema. So some of that stuff we talked about back in topic 8. And then we can get information from our second derivative as well. And this is what we were talking about in the previous set of notes, the 9.2 notes. Specifically, we can get information from the second derivative about the concavity of our function, and related to that, where any inflection points may be, if there are any. So again, there's really 3 functions we look at when we're trying to graph the function. The function itself, the first derivative, and the second derivative. So like I said, what I'm going to focus on right now in the next several examples is I'm going to focus on mainly information we can get from the first and second derivatives. Since this is a calculus course, it's not a curve sketching course. So I'm going to focus on the stuff that's really relevant to the stuff we've been covering in the past several sets of notes. But then I'm going to come back and do a more comprehensive coverage of all of these 5 bits of information in that very last example when we talk about curve sketching, actually sketching an entire curve from scratch. So I'm going to go ahead and actually just skip a lot of this for now. So I have information about all 5 of these pieces of the puzzle here. So the domain of the function, intercepts, asymptotes, first derivative and second derivative. But again, we're going to focus on looking at some of the above information, namely the first and second derivative, to see some features of our function. So these questions, apart from the very last one, are provided by Dr. Smith, who's a fantastic instructor in the math department. If you ever get a chance to take a class from him, I would highly recommend it. These multiple choice questions on the next couple pages are from him. And these are coming from old calculus exams, whether it was Math 249 or 265. So these are the types of questions to expect for things like the assignments or the lab tasks or the final exam as far as this curve sketching section goes. Because a lot of people kind of freak out and think we're going to make you sketch a whole graph by hand. On the final, we're not going to do that. it will be more like these kinds of questions that we're going to start seeing here on page 4. So let's take a look at this first one. And I actually think this is one of the dino problem questions from topic 9. So if you've seen this before, it just means you've been doing the dino problems. But we'll do it here together and see how to work through this. So in this example, 9.3.1, we're considering the following portion of the graph of the derivative of a function h. So this is really important. This is not a graph of h. This is not a graph of f of h. This is a graph of f prime of h. So it's a graph of the derivative. And we don't know what h is. We don't even know what its derivative is. We just have a picture of the derivative here. And what we want to do is we want to use this graph to make some sort of claims about the original function. Specifically, we want to figure out on which of the following intervals the original function, so h of x, is concave up. Now, initially this might seem a little tricky, and maybe we don't have enough information because as we talked about in the previous set of notes, the 9.2 notes, let me switch us to that really quick. When we talked about concavity, concavity was all about the second derivative, right? So we determined concave up versus concave down by looking at the sign of the second derivative. But we don't know anything about the second derivative here. We just have information about the first derivative. So the question then becomes, how do we use this and this graph to help us figure out concavity? So we don't have anything about the second derivative. We just have information about the first. So how do we determine concavity from a graph of the first derivative? Well, it helps to remember a few things, and some of this I just mentioned in the 9.2 notes. So I'm going to write some stuff down here that we talked about in the 9.2 notes. Specifically, I'm going to write down how we determine concavity from the second derivative. So from the 9.2 notes, sorry, my cat is sitting on my tablet. I got to move this really quick. Sorry about that. We learned that we can say that a function is concave up if that function has a second derivative that is greater than 0. And we learned that we could say that a function is concave down if that function has a second derivative that's less than 0. So that's what we learned about in the 9.2 notes. Now here's where we make a very important conceptual link. When we think about a function, remember that its first derivative describes the instantaneous rate of change of that function. And if we remember just talking about some function, let's say f of x, we saw that if f of x is increasing, that means its first derivative is positive. If the function is decreasing, that means its first derivative is negative. And so essentially what we saw is for an original function, the first derivative describes its rate of change. We also have briefly talked about the fact that the second derivative describes the rate of change of the first derivative. So just like the first derivative is the rate of change of the function, the second derivative is the rate of change of the first derivative, which is kind of a weird thing to think about, but it's actually going to help us link this graph of the first derivative to what we can say about concavity from the second derivative. So just like we can use the first derivative to describe if the function is increasing or decreasing, we can use the second derivative to describe where the first derivative is increasing or decreasing. And the way that we do that is exactly the same way we determine where a function is increasing or decreasing from its first derivative. So remember, we could say that a function, f of x, is, I'll use h of x just to be consistent here. H of x is increasing if its first derivative is greater than 0. So if we go back to the topic 8 notes when we talked about increasing and decreasing at the very end, it was all about the sign of the first derivative. And we said that h of x is decreasing if the first derivative was less than 0. Now, like I said, this same relationship holds for the first and second derivative. Namely, the first derivative is increasing if the second derivative is greater than 0. The first derivative is decreasing if the second derivative is less than 0. And so essentially what we can do is we can determine concavity by looking at our first derivative function and remembering this relationship. So we want to determine concavity. So we want to see what's going on with our function in terms of this. So we know that a function is concave up if the second derivative is positive, greater than 0. And how we relate that to the first derivative is we say, okay, well, we know the second derivative is going to be positive if the first derivative is increasing. So what this means is this implies that wherever our first derivative, h prime of x, is increasing, so has a positive slope, or has a positive slope, that means that the function is also concave up. So this is all about relating that relationship of increasing and decreasing to, instead of the function of the first derivative and the second derivative. So what I'm going to do here is I'm going to look at my graph and I'm going to see where my first derivative is increasing. In other words, where my first derivative has a positive slope. So if I go back to my picture here and just sort of trace along the picture, I can see that as I trace down, I have a negative slope in this first derivative until I hit this point. And then I have a positive slope, an increasing first derivative, until I hit this point. Then it looks like the slope of my first derivative is negative again until I hit this point. And then it looks like from there on, in this piece of the graph, my first derivative has a positive slope, or is increasing. Sorry, I'm getting my f's and my h's mixed up. So this is not h of x, this is h prime of x. Sorry about that. Okay, so what we just did is we showed where the first derivative, this picture, is increasing. We said that it's increasing on this interval here and this interval here. And we just mentioned that if the derivative is increasing, it means that the second derivative is positive, which means that's where we have concave up for the function. And so if I take a look at where these regions are from the multiple choice here, it doesn't look like I'm increasing from negative infinity to negative 3. This is negative 5, and this is 3.5 in terms of the x value. From negative 3 to 2, that's from here to here. Nope, that's not where we're highlighted. 2 to infinity, that's not where we're highlighted. Both negative infinity to negative 7 and 5 to positive infinity, so that would be this region and this region. That's not where we've highlighted, so that's not right either. Negative infinity to negative 3, that would be negative infinity to negative 3. And 2 to infinity, that would be here. So that's not what we highlighted either. So it looks like we're left with f. Let's just check and see if f is actually what we highlighted. So -5 to 0. That's exactly what we highlighted here, so that works. And 3.5 to infinity, so that's what we highlighted here. So that does look like it's the correct option. Those are the locations where the original function, again, not this function, not the first derivative, but the original function is concave up. So when we're doing these sorts of examples, it's always important to note what's being graphed. So here it was the derivative of h, not h. And so we had to use this picture of the derivative to assess concavity. Let's look at a couple more examples, a couple more multiple choice examples. So on page 5, we have an example that has 4 graphs of functions that can be differentiated twice, so twice differentiable functions. And we want to figure out which of the following graphs have exactly 2 distinct inflection points visible. So remember what an inflection point is. Let me go back here to the 9.2 notes again. So an inflection point, if we go, where was our inflection points? Here, at the bottom of page 3. An inflection point is a point where our function changes concavity, either from concave up to concave down. So here, these are graphs of my functions, my f of x functions, you can think of them. And what I'm going to do to determine my inflection points is I'm going to note where my functions are concave up and where they're concave down. So I'm going to color code this to make our lives a little bit easier. I'm going to use green to trace places where I have concave up parts of my functions, and I'm going to use purple to trace the parts of these functions that are concave down. Now I'm going to be eyeballing this a little bit just based on where I think the concavity is changing. So it might not be extra super accurate, but we should be able to assess the number of inflection points based on even just sort of eyeballing it from these pictures. So let's start with A. Let's just go A, B, C, D, and pick the one that ends up having 2 inflection points. So if I start with A, I can note that I have that concave down shape, that upside down cup or the frown shape, until I hit maybe right about there. And then it looks like my function switches to being concave up, or the cup shape beyond that. So it looks like on this graph I have 1 inflection point. I'll put a little star there. All right, let's look at graph B. So just like graph A, this looks like it starts being concave down. So I've got that frowny shape until maybe right about there. Then I switch to concave up, the cup shape, until maybe that x-axis again. Then I switch to concave down. And then it looks like I switch back to concave up. Maybe right around there. So how many switches do I have here? Well, it looks like I have an inflection point here, an inflection point here, and an inflection point here. So it looks like there's 3 inflection points on this graph. So here was 1, here's 3. Okay, so neither one of those has exactly 2. So let's keep going. Let's look at C. So C, again, looks like it starts out being concave down. So it's got that sort of shallow but still frowny shape until we hit, right about maybe there. And then we switch to the cup shape, the concave up shape. And again, I'm just sort of eyeballing this, so this might not be the most accurate. But we can see that it does switch to concave up at some point. And then it looks like, around the same place, it looks like a symmetric graph, almost a symmetric graph. It switches back to being concave down. along here. So how many switches do we have? We have one here. We have one here. So this looks like the graph we want. This is the one that looks like it has 2 inflection points. So that looks like what we want, but let's just check D and make sure that we didn't overlook one or we messed up on one of these other ones. So let's take a look at D. So again, it looks like we're starting concave down. And it looks like we have a pretty big concave down shape until maybe right around there. And then we switch to the cup shape, the concave up shape, beyond that. So once again, like plot A, it looks like we have a case where we have a single inflection point here. So it looks like in this case, the plot that has exactly 2 distinct inflection points is going to be plot C. I'm going to actually change this. We've been using blue as our answer, so let me just make that blue as well. Okay, so this one might not have been as bad as that first one, but again, we're looking at just the graph of the function, not anything about the actual function. We have no idea what functions produce these graphs, but we're looking at features about concavity, increasing, decreasing, all of those kinds of things. Okay, let's do a couple more. I'm going to move us here to page 6. And here we are looking at a graph of the, again, read carefully, the derivative of the function of f. And we want to figure out, based on this graph of the derivative, which of the following multiple choice questions here is true. So just to emphasize this is not a graph of f of x. This is a graph of the derivative, f prime of x. So we have to really be careful and not think of this as a graph of the function. It's a graph of the first derivative. Now let's look at our options here, and I apologize for the typo. I'll try to remember to fix that before I post these notes. That should be D. It looks like all of these options involve where our original function is increasing or decreasing. So it looks like the thing I'm going to have to look for in this graph of the first derivative is information about where the first, or how the first derivative tells us where our original function is increasing or decreasing. So I'm going to go back to the topic 8 notes here really quick, specifically the 8.3 notes, which is where we talked about where we have intervals of increase and decrease. And if we remember, going down here on page 2, our test for where a function is increasing or decreasing was all about the sign of our first derivative. Specifically, we said a function is increasing if our first derivative is positive, and decreasing where our first derivative is negative, less than 0. So that's really going to be the key here, because this is a graph of f prime of x. This is a graph of the first derivative. So let me just write down, actually let me move this. Move this over just a little bit, put it by the graph. Let me just write down what we learned about increasing and decreasing from the 8.3 notes. So we said that our function f of x is increasing when our first derivative f prime of x is greater than 0. And we learned that our function, that should just be f of x. We learned that our function f of x is decreasing when that first derivative is less than 0. So this graph, is a graph of the first derivative. And really what we want to get from this graph is we want to see where the function, the thing that's plotted, is greater than 0 and where it's less than 0. And for this particular graph, since this is a graph of the first derivative, what we're going to do is we're just going to see where this graph is above the x-axis, where it's positive, and where it's negative. And what that means is, in this picture, if our first derivative is up here above the x-axis, this is going to be where the first derivative is positive and is going to be the places where our function is increasing. Our original function, the one that's not graphed here. And if our first derivative graph shows up below the x-axis, that means that's where that first derivative is negative, which is going to be where our original function, not pictured here, is decreasing. So let's draw that on the graph as well. So it looks like we have a negative first derivative here. Then we've got a positive first derivative here till we hit that x-axis. Then it switches to being below the x-axis, so negative. And then over here, this is all above the x-axis, so this is positive first derivative as well. All right, now let's go through our options here and see what we've got. So I'm going to try to keep the graph as much on the page as we can as we go through. So let's start with A. F is decreasing on negative infinity to negative 1. So negative infinity to negative 1 looks like it's right here. Okay, that's true. It's decreasing. The first derivative is negative, so the function is decreasing. It's also decreasing according to option A from negative 1 to 1. Negative 1 to 1 looks like it's right here. That's not true. Our first derivative is not negative on that whole interval. So we don't have decreasing on that interval. So we can automatically here eliminate part A because we already said this isn't true. Let's look at option B. Option B starts by saying that f is increasing on the interval from negative infinity to 1. Sorry, negative infinity to negative 1. Well, we just said above, that's where we've got a negative first derivative, which means that's where our function is decreasing, so that's not true. So we can automatically eliminate option B. Option C is saying f of x is increasing on negative 1 to 0. So that's about there. That's correct. That's a location where our first derivative is positive, which means our function is increasing there, so that looks correct. And also increasing on 1 to infinity. So that looks like it's here to beyond. That also looks true, right? We've got a positive first derivative there, which again means that our original function is increasing there. So it looks like option C is the correct one, but let's do D and E just to check and make sure we've got the correct option here. So what about D? D is stating that the function is decreasing on negative 1 to 0 and 1 to infinity. Okay, well that's the same intervals as was in part C. So that was this interval and this interval. And we just said from part C that that's where we have positive first derivatives, right? That's where our first derivative is above the x-axis. And we just said if our first derivative is positive, that's where we have an increasing function. So in part D, neither one of these is correct. And so part E is none of the above, but we did just say that C looks like it's the correct one. So that automatically eliminates none of the above. So our answer here is C. Increasing on negative 1 to 0 and on 1 to infinity. Because again, that's where our first derivative is positive, and a positive first derivative, a first derivative above that x-axis, means that we have an increasing function on those corresponding points on the graph. All right, let's look at one more and then we'll do the curve sketching example at the end here. So I'm on page 7. Now again, read these carefully. Here's a graph of the second derivative of the function g. So this is not g of x. This is not g prime of x. This is g prime prime of x that's being graphed here. So nope, nope, yes. And we want to use this graph of the second derivative to determine which of the following options is true. All right, so if we look at our options, these look like they're all options about concavity, which is super convenient because the second derivative is the derivative that gives us information about concavity. And so what I'm going to do for this example is actually very similar to what I did in the previous example. I'm going to first write down what the second derivative tells us about concavity. Just like up here, I wrote down what the first derivative tells us about where our function is increasing or decreasing. So here I've got a graph of the second derivative. I've got information or statements about concavity. So let me go back to the 9.2 notes again, just to indicate where I'm looking, and write some things down about concavity and the second derivative. So if we look at page 3, we've seen this a little bit before already today. We say a function is concave up where our second derivative is greater than 0, and concave down where our second derivative is less than 0. So I'm just going to write that down here. Our original function f of x is concave up. Sorry, this is g of x in this example. Where our second derivative, g prime prime of x, is positive, and g of x is concave down, where the second derivative, g prime prime of x, is less than 0. Now again, this is a graph of the second derivative. It's not a graph of the function, it's not a graph of the first derivative, it's a graph of the second derivative. And so very similar to the previous example, what I'm going to consider is I'm going to consider from this graph the sign of my second derivative. Namely, if my graph, this particular graph is above the x-axis, that's where my second derivative is positive. And where this graph of the second derivative is below the x-axis, that's where my second derivative is negative. And again, if we draw that on our actual graph picture, we can see that it looks like maybe from negative infinity to negative 1, we have a negative second derivative. Then it switches to being above the x-axis from 1 to, looks like 0, sorry, negative 1 to 0. That's where our second derivative is positive. Then it looks like we have an asymptote there from 0 to, looks like maybe 1. We have another piece where our second derivative is negative. And then from 1 to, say, positive infinity, this piece, that's another place where our second derivative is positive. So let's use that and our options to see which of these options is the correct one. So the first one is stating, option A, g is concave up on negative infinity to 0. So negative infinity to 0 is this interval here. Now we can see immediately that that's not true because we actually switch signs for our second derivative there. So we're switching from actually concave down to concave up on that interval. So it's not going to be one type of concavity on that whole interval because our second derivative is changing signs from negative to positive, so that's not true. Option B, so that's out. Option B, our function is concave down on the interval from 0 to infinity. So that's this interval. And for the same reason, that's not true either, because we can see that the sign of our second derivative is changing from negative to positive on that interval, which means the concavity is changing on that interval. It's not going to be one concavity that whole time. So that's also not an option. Now, just a quick note, notice that this second derivative is concave up on negative infinity to 0 and concave down on 0 to infinity. But this isn't asking about the second derivative. This is asking about g. G is not the thing that's being graphed here. The second derivative is the thing that's being graphed here. So even though the graph of the second derivative has these concavities, the concavity of the second derivative doesn't have anything to do with the concavity of the original function. It's just the sign of the second derivative, whether it's positive or negative, that has anything to do with concavity for the original function. So that's why I'm stating that these are both incorrect, because these are statements about g, not g prime prime. So based on the information we have about the second derivative, g prime prime, we can say that these statements about the concavity of the original function are not true. Okay, let's look at part C. So C is saying g is concave up on negative infinity to negative 1. So that's this interval. And also on 0 to 1. So that's this interval. Well, that's opposite of what's going on. So on these two intervals, we can see that our second derivative is negative, less than 0 on the x-axis or below the x-axis. And when the second derivative is negative, that's in just concave down on those intervals, not concave up. So it looks like C is also out. But if we look at D, D is looking at those same intervals, negative infinity to 1 and 0, negative infinity to negative 1 and 0 to 1, and it's stating that the function is concave down on those intervals. And that is correct, because on those intervals we can see that we have a negative second derivative, and a negative second derivative indicates that's where our original function is concave down. So it looks like option D is our correct option here. So we do have concave down on the intervals where our second derivative is negative or below the x-axis. All right, so that is how we look at graphs of the first derivative or the second derivative, and we use those graphs to make claims about the original function. So again, when we get to these curve sketching examples, we have to be really careful with our reading. We have to make sure we know exactly what's being graphed, because we just saw in all of these examples, there was not a single case where the actual function was being graphed. We had the second derivative here, the first derivative. Well, okay, here I guess was the original function, but we were looking at concavity. And then here, the graph was of the first derivative. So it's really important, now that we're into talking about curve sketching and concavity and increasing and decreasing intervals, to make sure that the thing being graphed is known, whether it's the first derivative, the second derivative, or the original function. Because the information it gives us does depend on what it is. The first derivative gives us different information than the original function. The second derivative gives us different information than both the first derivative and the original function. So be really careful, read very carefully if you see any of these sorts of problems on like the web work or your lab tasks or the final or anything like that. Okay, so the last thing I want to do here is this is kind of a bonus example. Again, these are things that we're not going to focus on for this class as far as the important aspects of curve sketching, but this is the curve sketching set of notes, so I do want to do a full sketch of a curve based on those features that I mentioned briefly at the start of this set of notes. So what we're going to do, and again, we're probably not going to be able to do this in class because there's probably not going to be a time, whether you're in my section or Dr. Lee's section, but I'll do it here for anybody who's curious. So we have a function f of x that equals x minus 1 over x. And we just want to sketch this curve. I have some blank graph area down here for us. So what we're going to do to sketch this curve is I'm going to go back to way up here, page 2. And essentially what we're going to do is we're going to write down information from these 5 features. We're going to start with information we can get from the function. Then we're going to do stuff that's a little bit more familiar to us now, hopefully. Information about increase, decrease regions and extrema from the first derivative, and information about concavity and inflection points from the second derivative. Okay, so the first thing I'm going to start with is the domain of the function. And like I mentioned, on the next several pages, I just have some brief descriptions of these and how to find them, just because if it's been a while since you've sketched a graph or you haven't done some of these things, like looking at the domain or looking at intercepts, it's worth going over and seeing how to use those. So let's start with the domain. So when we talk about the domain of a function, we've talked about this, we just haven't really called it the domain very often. The domain of a function is all the values of x for which the function exists. In other words, the domain of a function is everywhere where the function is defined. Now I have a couple general types of functions listed here and their respective domains, just to maybe make things easier for us. So if we have a polynomial, we've talked about this before, polynomials are defined everywhere for all values of x. So their domain is all real numbers, all values of x, all real values of x. Rational functions, if we have something of the form a over b, the domain is everything that makes the denominator not equal to 0. So if there's anything that makes that denominator 0, that's not in the domain. That's not where the function is defined. If we're taking the odd roots of functions, so like the cube root or the 5th root or the 11th root, they also have the domain of all values of x, so all real numbers. And even roots, like the square root of something or the 4th root of something, the domain is all real numbers such that that inner function is greater than or equal to 0. So we've talked about this before. If we're taking the square root of something, we can't have a negative under the square root. Then we get imaginary numbers, and we're not dealing with that in this course. So we're confining ourselves to dealing with real numbers, real results. So even roots have to have an inner value, the thing you're taking the root of, that is greater than or equal to 0. So let's consider the domain of this function that we're going to graph. So I'll label this as the first piece of information, which is the domain. Now, if we consider this function and we think about where is this function undefined, are there any values of x that would give us trouble or make this function undefined? Well, x on its own is fine, but here we have a rational expression, 1 over x. And so if we think about what would make this denominator 0, well, if we plug in a 0, then we have an issue. We can't divide by 0. So the domain of this function is all real numbers except for x equals 0. Because that's the only thing that would make this function have an issue, that would make this 1 over something be 1 over 0. So all values of x except x equals 0. And that might not seem too useful yet, but we're going to see the usefulness of the domain in just a little bit as far as making some of our other calculations a little bit easier. So the second part, or the second feature that we can consider just by looking at the function itself, and I'll scroll back up to the top for this, are the intercepts. So when we talk about the intercepts of a function, there's two different types of intercepts we can have. X-intercepts, where the function crosses the x-axis, and y-intercepts, where the function crosses the y-axis. So to find our x-intercepts, what we do is we set our function equal to 0 and we solve for x. And for the y-intercept, what we do is we find the function at 0. So let's do our x-intercepts first. Sorry, we have to do so much scrolling. So let's start with the x-intercepts. So what I'm going to do is I'm going to take my function x equals 1 over x, x minus 1 over x, and I'm going to set it equal to 0 and solve for x. So if I solve this thing for 0, I'm going to get x equals 1 over x. Just setting those, subtracting or adding the 1 over x to both sides. And then I'm going to multiply both sides by this denominator x, so that's going to give me x squared equals 1. And so what values of x when they're squared equals 1? Well, x can be -1 and x can be 1. So these, let me put a different color box around these. These are my x-intercepts. And more specifically, our x-intercepts are the values of x where our function crosses the x-axis. So a little bit more accurately, let me rewrite this. Our x-intercepts are going to be the points -1, 0, and 1, 0. So these are my x-intercepts, just to be a little bit more accurate about them. Now my y-intercept, the way that I find my y-intercept is I find f of 0. Now we just mentioned up here that 0 is not in the domain of our function, which means we can't compute this. This is not going to be a valid value of our function. It's not going to be a place where our function is undefined. So for f of 0, we actually can't compute that, which just means that there is no y-intercept. So there's no place where our function crosses the y-axis. So once we get all these steps in, what I'm going to do is I'm going to sketch each piece of them in this graph so that we can see exactly what's going on where. But I'm just going to keep going through these different pieces and these different steps, and then we'll put them all together at the end. All right, the third piece, the third bit of information, this is the last bit of information that I can get directly from the function. That's the function's asymptotes. So we talked about asymptotes way back when we were introducing limits. And we mentioned there are two different types of asymptotes. There's the vertical asymptote and there's the horizontal asymptotes. So for vertical asymptotes, what we look at is we look at places where, or more specifically values of x, that cause our function to blow up to either positive or negative infinity. So we can define these in terms of limits. So we can say the value of a such that the limit as x goes to a from the left is blowing up to either positive or negative infinity, or the limit as x goes to a from the right is blowing up to positive or negative infinity. But the easier way to think about this when we're talking about functions that involve a rational expression is our vertical asymptotes typically occur at breaks in our domain when we're talking about a rational function. And so what I mean by that is if I go back down here and I consider this expression, we just said that this function is defined for all values of x except x equals 0. And so what that suggests is 0, because it's in this rational piece of this function, is going to act as a vertical asymptote. So I'm not even, you can verify this with the limits if you want to. Try to take the limit of our function as x goes to 0 from the left and from the right. But I'm just going to indicate, and we'll verify this with our work here in just a second, that we have a vertical asymptote at y equals 0. Now we also have our horizontal asymptotes. And we talked about this again back when we were talking about asymptotes way back in, I think that was topic 3, where we were dealing with asymptotes from looking at limits. And we mentioned that for horizontal asymptotes, let me go way back up here again. Horizontal asymptotes are another thing you can get from limits. Specifically, you just take the limit as x goes to negative infinity and as x goes to positive infinity of our function. So these are usually pretty easy to compute. We just need to take those limits as x goes to negative and positive infinity. So for our horizontal asymptotes, I'll actually do the limit calculation here for us. We're going to look at 2. We're going to look first at the limit as x goes to, let's do negative infinity first. So this is going to be the limit of x minus 1 over x. And this is a pretty easy function to take the limit of. If I just try thinking about what happens as x goes to negative infinity, this thing is going to go to 0, and the x is going to go to negative infinity. So as x gets smaller or larger and larger in the negative direction, my function is also going to get smaller and smaller in the negative direction. For my other horizontal asymptote, the limit as x goes to positive infinity of x minus 1 over x. And I get almost the same thing. This goes to 0 as I take this limit, and the x goes to here positive infinity. So technically, when we're talking about asymptotes and we get a number that is not finite, so we get either positive or negative infinity, we usually say that means there are no asymptotes of that type. So we just said that the horizontal and vertical the horizontal calculations here for these limits, they're negative and positive infinity. So another way we can say that is there is no horizontal asymptote. There is no finite value that these functions are going to start to approach. They're just going to blow up to positive and negative infinity as you go out in either direction. Let x get larger in the negative direction and y larger in the positive direction. So I'm just going to write that as no horizontal asymptotes. And again, we'll be able to visualize this and see exactly what this looks like and what this means when we're done. Okay, so that's all the information I can get from the function itself. The next thing I'm going to look at, so I've done the domain, the intercepts, the asymptotes. The next thing I'm going to look at is information I can get from my first derivative. So if I go back up here again and look at page 3, or I guess page 2 and page 3, So now I'm at part 4, information from the first derivative. This is again where I look at my intervals of increase and decrease and locate any extrema. So the way that we're going to use the first derivative here is we're going to sort of combine our two methods of looking for extrema and looking for intervals of increase and decrease. Because if we remember from the topic 8 notes, we had a very similar approach to finding our extrema and our intervals of increase and decrease. If we remember, in both the 8.2 and the 8.3 notes, we did this thing where we found our critical and singular points, and then we made this little number line thing where we looked to determine not only extrema, but also intervals of increase or decrease. So I'm sort of going to combine that information all here in step 4 of this process. So let me scroll all the way back down here. Step 4. So this is where we look at the first derivative. So because I'm going to need the first derivative, I'm of course going to want to calculate the first derivative. Actually, let me write down our function so we don't have to keep scrolling back up. Our function was x minus 1 over x. So I'm going to write that as x minus x to the negative 1, just to make my derivative a little bit easier to calculate. And I'm going to calculate my derivative, f prime of x, as the derivative of this thing. So 1 plus x to the negative 2. That's my first derivative. Or 1 plus 1 over x squared, same thing. So here's my first derivative. And I'm just going to write down a couple things about this first derivative. I'm going to note any critical points and any singular points. So my critical points, again, these are the points where my first derivative is equal to 0. So 1 plus 1 over x squared equals 0. And if I solve for that, I get 1 equals negative 1 x squared. Which gives me, multiply both sides by x squared. I get x squared equals negative 1, which I can't have, so I don't have any critical points here. So there are no critical points that could possibly be extrema. Singular points, however, if I consider my singular points, remember that my singular points are places where my first derivative is undefined. So where is f prime of x undefined? Well, my first derivative is 1 plus 1 over x squared. Sorry, I had accidentally hit the pause button on the record, so I don't know where I stopped. So I'm just going to keep talking from where I think I stopped. I'm so sorry about that. I think I was talking just through the critical point process, the singular points process. So our singular points are where our first derivative is undefined. So this is sort of like where we were looking for the domain in the original function, right? I'm looking at my first derivative now, and I'm saying, okay, what would give me issues with this function? Or more specifically, since we have this rational piece, what would give me a 0 on my denominator? Well, it looks like I would have a singular point at x equals 0. Because if I consider x equals 0, that's going to give me a 0 on my denominator of that piece of my function, which is something that I don't want. So it looks like I have a singular point at x equals 0. So now what I'm going to do is I'm going to use my points, in this case just my singular point, and I'm going to make that little number line, put 0 right there. And what I'm going to do is now I'm going to use that first derivative to determine where my function is increasing or decreasing. Specifically, I'm going to look at this interval and this interval. So here's my first derivative, that 1 plus 1 over x squared. So let's consider this interval. So for values of x less than 0. And I'm just going to plug into my first derivative here a negative 1. So I'm going to have 1 plus 1 over negative 1 squared. And remember, all I care about here is the sign of my first derivative. And this is going to give me a positive value. So on that interval, this is telling me that my function is increasing. Let's look at the interval x greater than 0, the blue one that I've written here. Nice easy number on that interval to plug into my first derivative is just plain old 1. So that's going to give me 1 plus 1 over 1 squared. That's also going to be positive. So actually what we've done here is we've used our information about our critical points, which there were none, and our singular points, which was just this x equals 0. And we found, by using the first derivative test, that this function is actually increasing everywhere. So remember, with the first derivative, we get information about where our function is increasing. So I'm going to say here as my conclusion for my information about my first derivative, I'll say by the first derivative test, my function f of x is increasing everywhere. So the only possible place where my first derivative could change signs is at 0, but we just showed that the first derivative has the same sign on either side of 0. Namely, it's positive, so we can say that the function is increasing everywhere. Okay, we're almost done. Hopefully I'll have enough room to write this on here. I should have put this graph on the other page, but I didn't. I'm sorry about that. But if we don't have enough room, I can just scroll down a little bit more. The fifth and final piece of information is information we get from our second derivative. So we're finally to step 5 of this process. And now we're going to look at concavity and the location of inflection points for this graph. So specifically, we're going to look at taking our second derivative and then assessing the sign of the second derivative to determine concavity. So first thing I'm going to do is I'm going to find the second derivative. So our first derivative, let me just write this down here for us so we don't have to scroll. That was this. That was 1 plus 1 over x squared. I'm going to rewrite that fraction as 1 over x squared. That's the same thing as x to the negative 2. So again, I'm doing that just to make my life a little bit easier when I take my derivative. So my second derivative is the derivative of this. So f prime prime of x is going to be derivative of 1 is 0. Derivative of x to the negative 2 using the power rule is going to be negative 2 times x to the negative 3, which is the same thing as negative 2 over x cubed. So that's my second derivative. Okay, so now what I'm going to do is I'm going to try to use the second derivative to determine concavity and inflection points. So if we remember how to do this from the 9.2 notes, let me just scroll down to our process here. We're going to find possible inflection points by setting our second derivative equal to 0, solving for x. That's places where our concavity may change. And we're going to find any places where the second derivative is undefined. Then, just like we did for the first derivative, we're going to create intervals using these points, and then check the sign of the second derivative on each of those intervals. So I'm just going to keep going here. I'm sorry, we're a little bit off the page. So first thing I'm going to do is I'm going to set my second derivative, negative 2 over x cubed equal to 0, and solve for x. And this is specifically to find possible inflection points. Okay, so if I try to solve this thing for solve this thing for x, I can multiply both sides by x cubed. That gives me negative 2 equals 0. That can't happen, which basically just means we don't have any inflection points. So there's no places where our second derivative is defined where the concavity can change. However, concavity can change around places where the second derivative is undefined. So just like we did up here with the singular points, we looked to see where the first derivative was undefined, and we used that point actually to construct our two intervals. We do a similar thing with the second derivative. So not only do I need to look at inflection points, but I also need to look for places where my second derivative, negative 2 over x cubed, is undefined. And again, it looks like I'm running into x equals 0. That's a place where my second derivative is undefined. And so what I'm going to do is just like we did for the first derivative, I only have one point of interest here. I don't have any inflection points. I have one point where my second derivative is undefined. So I'm going to use that point to create two intervals. And I'm going to check concavity on these intervals by checking the sign of the second derivative on these intervals. So very similar to what we did with the first derivative, except in the first derivative case, we were assessing increasing and decreasing intervals. Here we're assessing concavity on these intervals. So let's do the same process. Let's use the same numbers even. The second derivative at negative 1 is going to be negative 2 over a negative 1 cubed. Negative 1 cubed is going to be negative. So we have a negative over a negative, which is going to give us a positive second derivative on this interval. Now for our second interval here, for values of x greater than 0, let's use 1 as our point. So we have negative 2 over 1 cubed. 1 cubed is positive, negative 2 is negative, so that fraction there is going to be negative. So even though we don't have an inflection point, we do have a point where our concavity is changing. It's changing around that place where our second derivative is undefined. So we can say here, our function is concave up where our second derivative is positive. So it's going to be concave up on the interval negative infinity to 0, and concave down where our second derivative is negative on the interval from 0 to positive infinity. Okay, so that was a lot of work, but we got a lot of information about this function. So let's go ahead and just start drawing what we have. So the first thing I'm going to draw are my x-intercepts, so -1, 0, and 1, 0. -1, 0 is here, 1, 0 is here. So those are going to be points where my function crosses the x-axis. I don't have a y-intercept. We'll see how that looks in a second. Next thing I'm going to do is I'm going to draw in my asymptotes. So my vertical asymptote, sorry, that should be an x, is at x equals 0. And I don't have any horizontal asymptote, so I'm just going to draw in my vertical asymptote at 0. So I'm going to draw that, and you usually see this in graphs this way, as a dotted line at 0. So this vertical asymptote is in this case is the point where our function is undefined. And so what we're going to see with the other information in this plot is we're going to see that our function is not going to cross this y-axis or this particular intercept. Okay, so we know that basically we're going to have two contained pieces of this function, one on the left of that vertical asymptote and one on the right. So let's see what else we can get from this particular information to draw our function. So by the first derivative test, our function is increasing everywhere, which means wherever we draw our function, it's going to have a positive slope. It's going to have some sort of positive slope to it on both sides of this vertical asymptote. And we're also told that there's no inflection points, but we do have a switch in concavity about that vertical asymptote. Specifically, our function is going to be concave up to the left of 0 and concave down to the right of 0. Now that may still not seem like a lot of information, but if we think about the limitations that this gives us, it actually gives us quite a bit of information about how this graph looks. So let's start with this side of it, so the side to the left of our vertical asymptote. On this piece of the graph, the function is going to have to be increasing and concave up. So if I think about what that looks like, so concave up has that sort of cup shape, and increasing is a positive slope. So I have to pass through this point. So one way that I could draw an increasing concave up function on this side of the graph would be maybe something like this. Or let me just make that a little bit more clear that this is a vertical asymptote. Maybe I'll draw it like this, where we can see that the function, sorry, I'm really bad at drawing on this tablet, we can see that the function is not going to hit this line. It's going to get closer and closer and closer, but because it's a vertical asymptote, it's not going to cross that line. So that's increasing, positive slope, concave up, the cup shape. Now I'm going to consider this side of the graph separately because I know I can't connect this to anything over here because that's a vertical asymptote that we're dealing with. So what does this side have to look like? Well, it also has to be increasing, so it's going to have a positive slope, but it's going to be concave down. So if I think about what that looks like, so I still have to have this positive slope, but now it's concave down, so it's going to have that sort of a shape. I might have something like this. I'm really bad at this, I'm sorry. Something like that. Where again, I'm treating this as a vertical asymptote, so my function is not going to hit that or touch that. But I still have a function that is increasing, positive slope, and now has that frowning shape, that concave down. So it's a pretty basic looking graph, but we can double check it with an actual visual if we want to and see what this looks like. So I've got Desmos open here with the actual graph of this function. So let me go ahead and move that over here so we can see how close this looks. There we go. Okay, so maybe if I zoom in here a little bit so it looks kind of like what we've got on the page, something like that. So yeah, that's not too bad, right? So just based on the information from calculus and a little bit of information from the function itself, we got a decently accurate picture. So it is just a sketch. It's not super accurate. We didn't plug any actual points into our function apart from 0, and the function was not defined at 0. But we're still able to get a pretty good picture of this function. And part of the reason that we were able to draw it so specifically, even without additional points, is because those concavity pieces actually limit how these sides can look. Like there's no way I could draw another concave down image here and not have it run into the vertical asymptote, for example. So there's not really a way that I could draw this where I have both an increasing function and concave down without it running into this somehow. So I'm limited by this vertical asymptote and by the concavity and increasing structure of this piece of the graph. Same thing here. I'm limited to how this can look by the vertical asymptote, by the fact that it's increasing, and by the fact that it's concave up. So if we tried to draw other versions of this in this graph, we would run into the issue where our graph is going to run into that vertical asymptote, which can't happen. So because of the limitations of the way that the vertical asymptote works with the concavity and with the increasing and decreasing, this is really the only way that this function could look based on the information that we have. So again, with curve sketching, we're not going to ask you guys to do this sort of a thing. I think I'm going to have some examples of this in case anybody wants to practice sketching some curves. But it's more going to be this sort of thing where the important thing is to know what the second derivative is giving you, what the first derivative is giving you, and know how to read graphs of the first derivative or graphs of the second derivative to get information about the original function, which may not be pictured or may not be known.